record this so that we have it. I'm going to try to remember to record all these from now on and get the video to save properly. Now, there are a good number of y'all that actually got the correct answer, which is awesome. Good job. The way that I went about it, because I think some of y'all went about this differently, is I actually drew this out. So we have 5 congruent squares. Let's see if it'll let me draw. So 1, 2, 3, 4, 5, and it makes a plus sign. Now we know that the sides of a square are all congruent, and their perimeter is 72. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So all 12 of these sides will add together to be 72. And as a good number of y'all wrote, we can take 72 and divide by 12, which would give us 6. So all the side lengths for all these squares are 6. So to find the area of each individual one, get a different color, would be 6 times 6 is 36. So each one of these is 36 square centimeters. Well, I can add it together 5 times or do 36 times 5, which actually gives us 180 centimeters squared. And I mean, there's different ways that we could have done it, because you could draw it out and see it that way, or if you know that the perimeter and counted it up and saw that it is 12, divides 72 by 12, find the area of one to find the area of the rest. And a lot of times, if drawing it out helps, go on and draw a picture to represent it. All right. Any other questions on the entrance ticket? Okay, so let's put the computers away, and we'll go on and look at the lesson today. So this here is just another kind of explained out way to do this. Probably a little more confusing than seeing it walk through. So what we're looking at today is calculating the area of geometric shapes. Find the dimensions of geometric shapes with given areas, going from one to the other. Now, a ratio is one way to compare two numbers. Compare two things. It's an expression that measures how two numbers relate to each other. It can be written with a colon or as a fraction. So we can say 1/2, 4, or 1/4. And this is really just the same as kind of 25%. So for every one of one thing, we have 4 of another. So we can say, what is the ratio of boys to girls in the class? Well, if we count it up, because we have 4, 8, 9, 10, 11 girls to 4 boys. So we could say 4 to 11 or 11 to 4, however we want to do that. Now this specifically here, these ratios here are considered part to, what do y'all think? Part to part, because the number of boys and number of girls, neither one is the whole. We're not talking about the whole class, because its number of boys is still part of the whole, and the number of girls is still part of the whole. So if we actually wanted to consider it part the whole, we would say that the number of girls would be 11 over 15, and the number of boys would be 4 over 15, or 4 to 15, 11 to 15, part the whole. Any questions on this here? Well, we could change it a little bit, because that would just change it to 11 or 11 to 5, because I didn't include myself in the first count. And that's how we can kind of consider ratios. And these ratios are actually very helpful if we're thinking about areas or relating two different shapes. Because we can say that the sides of a rectangle comparatively are 2, 2, 3, and the other sides are 4, 2, 7, or we need it in that aspect. So we can look at the perimeters and areas accordingly if we have the dimensions of the ratio. Now, do we remember what the area of a triangle is? That'd be the sum of the interior angles. 1/2 of the base times the height. And the height is always going to be like the distance from the one of the vertices or the vertices to the other side and forms a right angle. Now, if it is a right triangle, the base and height are always going to be the two sides where the right angles form. Now, for the most part, for these here, trying to find the height is either going to be given most likely, because we put it in like a square. The height of the square is going to be the same as the height of the triangle. Because to find it otherwise, we would have to go into sine, cosine, and tangent, and using those properties to find the height and base. All right, let's look at another one. Area of a rectangular square. Or base times height, length times width. Because we're taking our two dimensions and multiplying them together. All right, we ready for a tricky one? Parallelogram. So I can draw a picture of a parallelogram. Kind of like this here. Parallelograms, two sets of parallel sides. Base times height, same thing. Parallelogram does not have to have 4 right angles. Rectangle and square do. So we can have this kind of slanted figure for it. Yeah, a rectangle and square are a parallelogram, but not all parallelograms are rectangles or squares. Now, the best way I can demonstrate this is with paper. So this here, everything's lined up straight, yes? So, not three-dimensionally, but this flat side we can call a rectangle, yes? So the area of it would be length times width. Now, for a parallelogram, what I can do is shift it over. Well, is the area still the same? Yeah, because the space that I have cut out over here is actually going to be the exact same as what's cut out over here. And they do that as a more rigorous proof of this for this kind of shape that, a different color. No, unfortunately, kite is not. But these two sides over here, so the area that this is would actually match up to the area of this piece here. So I can almost take it and move it over there and actually get back to this rectangle and have the exact same area, or vice versa. Yep. So we end up getting the exact same, and I could go through the proof of it, but that would bore you all to tears. Because it would be talking about this as side length A, and if we talk about this as side length kind of X, and I can show that the area of the triangle here is actually the same as the area of the triangle here, so the overall areas don't change. I think so. But the parallelogram, rectangle, and square actually do have the same areas. Now the next one we have is trapezoid. Trapezoid's a little bit funky because they have it written here as base 1 plus base 2 divided by 2 times the height. I think the way that you all are used to seeing it is 1/2 of base 1 plus base 2 times the height. For a trapezoid, we add the two bases together and multiply it by the height. Now, if I remember this correctly, this is really dealing with the manipulation of the parallelogram area formula and our, I'll put those up, the shapes themselves. I'm going to draw this on the whiteboard because I have a little more space at this point. Is that we can take a trapezoid here and flip it and add it back to itself. Base, base 2, or that'd be base 1. This would be base 2 and base 2, which would mean that the overall length of this here and this here would be the exact same. And these distances over here, so the two sides, would actually be the same, and the properties of a parallelogram would hold true. So the overall width here is B1 plus B2, and the height we'll call H. So for this here, if we talked about it as parallelogram, would be the height times base 1 plus base 2. But how many trapezoids do I have now? 2, but we'd only want the area of one of them, yes? So I'd have to take this and half it. And that's kind of how they get to the area formula of a trapezoid. Questions on these here? Now, if the ACT is nice, because on some of them they will provide some of the area formulas to you. And for some of the trigonometry equations, not this one, but like this here, the law of sine of A over A, sine of B over B, sine of C over C, or law of cosines, which I have it posted on the back wall. I need to switch law of tangents and law of cosines. A squared is equal to B squared minus C squared minus 2BC cosine A is another one that will pop up. We won't focus too much on it because on average it shows up for 1 or 2 questions. So if you're shooting for 36 out of 36, those are good to study and see. But right now, if y'all are trying to get up above 20 or higher, they're not as important. Okay. We've been skipping most of these activities, but I'm going to try implementing them to see. I think y'all enjoy some of the activities more with these here. Because 11.31, understanding area, has a big blank space, yes? So, we're going to turn the classroom into, it says an epic walk-in closet. I'm just saying we're going to try to update the floor. I mean, it doesn't need updates, right? I mean, there's nothing wrong with this flooring. Yeah. So, 2 little holes. So, if we wanted to update the flooring in here, well, most carpeting or flooring is all done in what? Area, yes, because we're all done by square footage. So, if we wanted to updo the carpet or redo the flooring, what's one of the first things we'll need? The perimeter, the square footage, so that we can find the area. As we had 6 foot, 19.8, 31.8, 22.6, 25.8, and lastly 2.8. Now, when we did this the first time and actually talked about wallpapering, or talking about the perimeter, because we'd actually need the overall height of the walls, which I actually did take and actually do know. Not off the top of my hand, I do have it in the filing cabinet. We got a little trick when we did perimeter because we could ignore this kind of space over here, because we could act like it wasn't there and go on and get the perimeter quite easily. Exactly. But can we do the same thing for this here? Yes. As if we could find the area of this section, we could subtract it from the area of the whole. Or we could have broken it up into squares and done the exact same thing. Well, the area, if with that included, would be doing what? So the overall length is 22.6 feet, yes? The overall width is what? 31.8. So we would need to multiply those two together. And as much as I would love to multiply those out by hand, I don't quite have the space. So with that included, with that little section included, we have 718.68 square feet. Now, if we find the little extra set over here, it would be what? 2.8 times 6. And 2.8 times 6 is 2. No, it's not 2, it's 8. 4, 12, 16.8. So to actually get the correct square footage, we have to take 718.68 and subtract 16.8 square feet from it. 8, 8, 7, 1. So if it measures out to about 701.88 square feet, how many square feet do we need to order? 702 at least. Because if anybody's done any projects, it's always better to order a little more than it is less. And I've helped a friend do flooring before, and he bought way more because, heck, if you don't open it, you can always return it and get your money back. It's always harder to try to get more of it than it is to send it back. So 702 square feet. Well, if it costs $15 per square foot, how much is it going to cost us? 15. If it was $15 a square foot, I'd be happy with what we got. Because that's a lot of money to redo this little area here. But luckily, it's not normally $15 per square foot. Could it be $15 a square foot? Yeah. I mean, you could probably get real red oak for probably that much, or probably get a good deal on it for 15. Yeah. 8.8. Yeah. It doesn't do us a whole lot of good to save that extra little bit. Yep. And that's also probably why a lot of places go to stained concrete, if y'all even know what that is. Yeah. Yep. All right. Let's look at the next one, because I think the next one already gives you a diagram. So, we have this diagram here. So, what do you need to know to find the area of this composite shape? What would be nice? Perimeter, area, or lengths. Yes? So, I'm going to give you 3 lengths. So I will tell you, and we'll say that the length of AH is 2. The length of EF is 8, and GD is 4. And it is 3. So let's find the area of AB CD. I'm going to write this up here. You can write it in the space below that box that's given to you. You can fill the area stuff in as we go. Because I don't want to go to the next slide and take this shape away. So what is ABCD? AB, the whole rectangle, yes? So our height or length is, what can we say? 3. And the other length would be 2 plus 8 plus 4. So 3 times 14 is, so the overall area of the entire shape is 42. Now say we want to find the area of triangle HAE. That would be what? Or 1/2 or over 2. Hopefully y'all can do that one in your head. Because our 2 times 1/2 is 1. And 1 times 3 is 3. What's the area of triangle BAE? Because those 2 triangles are the same. Pythagorean theorem? That'd find missing links, yes. So we'll get there in a second. What would be the area BEHA? 6, yes? Because we could do that by saying 3 times 2 the area of the rectangle, yes? Well, we found the area of this one is, and the area of this one is, well, both those triangles compose the whole square, yes? So 3 and 3 would be 6. All right. I need an eraser. You're feeling that Jeremiah. Yes, please. You good? Yes. 100% focus the whole time, yes? So let's find the area of E, F, G, H. It'd be what? It'd be 8 times 3, which is? Here, this is triangle FDG. It would be 1/2 of 4 times 3 or 3 times 4. Half of 4 is 2, and 2 times 3 is. So what would that mean for triangle FCD? Also 6, yes? Now, with all this information given, I'm going to erase this here because I do have it written onto the figure for all these areas. Do we know the 2 diagonals given? Let's get a nice copy. Do we know what either one of these are? I mean, we could find them, yes? How about the area of the figure AEFD? That trapezoid. So 1/2 of 8 plus, well, 14, as we said earlier, times 3, yes? That would be 1/2 of 8 plus 14 is. Well, 1/2 of 22 is 11, and 11 plus, or 11 times 3 is. So the area of that trapezoid is. So did we need to know either one of those diagonals? No. Yep. And we would have gotten there the exact same way. So if we're given different figures and composite shapes, we can actually work our way to getting there. If you're given a complicated shape on the ACT, you don't remember the formula for it, you can divide it out like we just did here into rectangles and triangles for easier calculations, or draw it out. Let's see here. Go back one page. Did we say any of these sides were congruent? Did I say that any kind of properties of the shapes themselves? No. Luckily on the ACT, unlike my geometry tests, the shapes, if they look to be similar, the side lengths look to be similar, they're most likely are. The shapes are going to look similar to what they are. They're going to draw them to scale. So all the shapes on the ACT are drawn to scale how they should look, which is helpful so it's not misleading or misconstrued. That it doesn't look like it should. For I think most of y'all that took geometry remember that. You would get angles that look like this here that worked out to be 98 degrees, or an angle that looked like this here and was 20. So the shapes and angles do look like they should. So that is something helpful. Now, we're stopping here.